All right, so YouTube should be on right about now. There we go. And we also know that the Google Translate app can actually do it in real time. So somebody can, so it can act as the translator between two people in real time, which is kind of cool. All right, so it is time. So I'm gonna get started with today's lecture. So the way the class is set up, at least for the time being, is okay. What was I about to say? Oh, right. So the lab is actually part of the structure of the class. So when you're doing the lab, you're actually studying as well in the class for the time being. So let's go back to the modules and we'll take a look at where we are at this point. So today is the due date of the LDST and LDI lab. If you guys have any questions, we can talk about it. But if there are no questions about it, I would just kind of not talk about it. The one that is due next Tuesday is simple branching and code analysis. So I'm going to introduce some additional ways to kind of extra techniques to work on that lab. And we got some questions coming, so I'm going to wait a little bit before we get started. All right, so there might be some questions about the lab that was just due. So let's go take a look at it. And it's probably a good idea to start up Logisim on the side. And let me get it started. There we go. All right. All right. So, okay. So let's go ahead and work on that lab. We may or may not need Logisim to work on that lab, but we'll see. So I'm going to go on to preview, which means I'm going to work on the questions just as you do. And I haven't really gone back to these questions for many semesters for sure. So these are all kind of new to me at this point. All right, so the first question is the LD instruction loads content from RAM to a register. The RAM location is specified by another register. The general format is LDX in parentheses Y, where X is a register A, B, C, or D, and so is Y. Note that X and Y can be the same register. Look up the opcodes table and find out the actual binary opcode of the following mnemonic. Load C from where D points to. Okay, so that's basically the long way of saying it, is to load C with whatever D is pointing to. Do not include any space. The answer should have exactly 8 bits. Okay, so we want it to be in binary, which means it has to be in zeros and ones. So for this question, there are several ways to do it. The first way is to just put this into the assembler, let the assembler figure it out, and then go to the assemble tab, look at the hexadecimal number, and translate that into binary, and then put it here. That's one way to do it. It's not wrong. It's perfectly okay. And the other way is to look up the opcode table and find LDXY, which is right here. And we want XX to be, I cannot remember. We want XX to be, oh, no, not this one. I cannot find my stuff. Okay, gotta close some extra tabs. There we go. So we want X to be C and Y to be D. Okay. C is the third register, which is 1, 0, because we count from 0. So XX is 1, 0, YY is 1, 1. So we have 1, 0, and then 1, 1 over here. So the answer is going to be 1, 1, 1, 1, 0, 1, 1. So let's go back to the quiz. I'm going to put it right here so it's right next to each other. So it's going to be 1, 0, 1, 1, 1, but the leading 0 is going to be forgotten. It's going to be ignored. And then 1, 0, 1, 1 is the other half of the binary number. All right, so next is question number 2. So there are a few questions about question number 2 and question number 3. I actually did not try to make it confusing. Despite what some people think, I did not actually intentionally make it confusing. So let's go ahead and read the question. In question number 2 is asking, now start up LogicSim and load processor 0003.circ. In the ROM component, what is the address of the first microcode slice to implement this particular mnemonic? State your answer in hexadecimal digits without the 0x prefix, and use all lowercase in the number. All right, so the first thing is, what exactly is a slice? Now, I do believe that I mentioned that in class already, that a slice is no more than a location in ROM. So microcode is already suggesting that we are talking about something in ROM, and slice is basically just saying a location in ROM. So we're talking about a location in ROM. But the most important part is the question is asking what is the address of, okay? So I'm not asking about the content at that location. I'm talking about the address of the location. Then the second word that is also important is the word implement. So, okay, Aiden has got a question. Okay, to answer Aiden's question in the text channel, it's because I want to follow the standard of C. Whatever is on the left-hand side, in this case, Y in parentheses, is the one that is updated. So the update always go from right to left. That is why it appears to be backward. But if you look at which side is getting updated, it is always the first operand that is updated. So there is a rationale, in what appears to be backwards. All right, so let's go back to the question here. So the keyword here is to implement. In other words, even though the execution of every single instruction starts with fetch, followed by a decode, but the microcode slice to actually quote unquote implement is the location that is specific to this particular instruction. Okay, so that is basically where we are decoding to. Okay, after the decode, where do we go in ROM? That is that's what the question is asking. I just want to point out, I totally neglected this part too. The question itself also suggests that we need to look in the ROM. Why? Because the first part of the sentence says in the ROM component, and I missed that too. So definitely we're looking into the ROM, and we're looking into the address, and we're looking at the one thing that is specific to LDCD. Now, I really don't know how else to ask this question. How else to associate the location that is in the ROM that is specific to LDCD, other than using the word implement. I suppose I can use, okay, where do we decode to, in the ROM? And that's the other way to describe it. So the way to answer this question is you don't even need to use LogicSim. You can if you want to, okay? But to answer this question, all we have to do is to look at this, okay? This is a 7, and this is a B. So the location in ROM is 7B0. The 7B is coming from the instruction register, and the 0 is coming from a constant of 0 when we perform the decoding of the opcode. So that is why the answer to question number 2, I think, is 7B0. And let me just double check. Yep, I think that is the case. That is correct. If you do not add the extra 0, it is not an address in ROM. So the 0 here is crucial because without the 0, 7B is the opcode, but it is not an address in ROM. Yep, you almost got it. I think you understood some of the concepts, but you're forgetting that an address in ROM has um, has that extra zero. Basically, has 12 bits and not just 8 bits. All right. Unfortunately, with these, there are no partial credit. So, all right. Yes. Okay. So that question is telling me that we are perhaps neglecting why that zero is there. That zero is coming from this constant of zero, which then becomes bit 0 to bit 3 before we use that bit pattern to update the microcode pointer. So that's why there's always an extra zero here when we decode and opcode. So to address the question, it's important to understand why we have that zero. It's not just that, oh, okay, now we know there's a zero. Okay, that part is not important, not nearly as important as understanding why there is a zero as the least significant hexadecimal digit. All right, so let's get back here. Okay, so LD is a simple instruction. It is implemented by a single slice of microcode, so same term used in the previous question. Look up the ROM of the processor and find out what is the first slice of the ROM of the microcode of the LDCD instruction. State your answer in hexadecimal, all lowercase, and without the 0x prefix. So this time, I do have to go to Logisim, because as much as I can figure out everything without looking it up, it's so much easier to just to look it up. So we'll go to edit content, and because my screen is large, so it decides to open this window like super huge, and I just shrink it back to a reasonable size, and now we go to 7B0. So 7B0 is right here, and this is what we need to type as the answer. So it is 1503056. I don't think copy and paste works, so you probably just have to kind of really type it. All right, so I'm gonna put this off on the side so I can see it when I'm typing. All right, so let's go back to the quiz, and the answer is 1503056. There we go. All right, so question 2 and 3 are closely related. One is asking about the address, as the question itself, states quite clearly that we are looking at the address. And then the other one is looking at the content at that address. So this time it is asking what is the first slice. It is not asking about where is the first slice or what is the address of the first slice. It is asking what is the first slice, and one slice is a location in ROM. All right. So I'm not seeing any questions. We are moving on. So we are now moving on to question number 4. So question number 4, says, okay, now we're moving on to the ST instruction. So in this case, the value of register X, okay, which is the second operand in this case, is copied to the RAM location pointed to by register Y. So we're treating Y as a pointer. Whatever location in RAM is pointing to is now going to be updated by register X. Again, X is one of the 4 registers, A, B, C, or D, and Y can also be any one of the same 4 registers. And I'm asking how many variants are there to the ST instruction. In other words, how many ways can we combine registers for X and Y? So STAA is one, STAB is another one, and so on. So we can see that they are independent because which register I choose for Y has nothing to do with which register I choose for X. So the answer is 4 times 4, which is 16. And if the question does not indicate what base we should be using, the default is 10. So we're using base 10 or decimal here. Question number 5. So question number 5 is about labels. We talked about labels in class sometime on Tuesday or last week. I think it was last week. The assembler accepts label definition. This is handy, blah, 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 blah. And the question is asking about, assuming the above code is at the beginning of a program, what is the label represented? What is the value, excuse me, what is the value represented by the label L2? The first instruction, the first opcode is going to take up 1 byte. So byte 1 is where label 2 is labeling. So the answer is just 1 in this case. Question number 6. Labels can be used as an immediate value. This means the LDI instruction can use a label as the I part. This is quite handy because very often we need to get the content from a specific location in memory, and labels or symbols make this easy. All right, so we have this code here. When the program gets to the halt instruction, what is the value of register B? Specify the answer as an 8-bit with leading zeros, if necessary, binary number. Okay, so with this one, you also got a few choices to answer the question. You can just run it, okay? You can just run it in Logisim, when we get to the halt instruction, which is indicated by the halt pin being a 1. Then you can stop simulation, and I believe register B appears as an output pin in the main part of Logisim. Then you can just copy those bits into this space over here. That's doable, okay? But for those of you who want something a little bit more challenging, and also to apply what you have learned so far and see if we can solve the problem in a slightly different way, you can actually solve this problem without using Logisim at all. And that's what I'm going to do next. So the first thing is to understand what the program is doing. The first thing it's doing is it is loading whatever value L1 is into register A. But what exactly is the value of L1? L1 is the address of the ST instruction. In other words, after the first instruction, register A will have the address of the ST instruction. Now, that's just an address, okay? And exactly where is that instruction is not even important, okay? So the second instruction, which is LDBA, is going to dereference register A, which at this point has the address of the ST instruction. So it's going to dereference the address to get to the content. So the actual opcode at location L1 is now going to be used to update register B, and then we get to the halt instruction and the program stops. So this means we never execute, the ST instruction in this program. We never got to execute that particular instruction. We are only trying to get to the opcode of this instruction here. So now the question is really just doing the assembling of this particular instruction that is a mnemonic, and we just want to convert it into opcode or into a binary opcode. So now we have to look up the opcode table. Go to the ST portion. So we got LDI, LD, and further down somewhere is ST. So here's ST. So we can see in ST, XXYY, is kind of reversed of, how X and Y appear in the mnemonic. And once again, the reason why it is reversed in the mnemonic is because I want to maintain the standard of the first operand, which in this case is Y in parentheses, is the one that is getting updated. Okay, so I want to keep that consistency. All right, so and as usual, I have forgotten the actual instruction already. So it is STAD, okay? So D is X, so X is 1, 1, and then A is YY, and that means YY has to be 0, 0. So the whole thing becomes 1, 1, 1, 1, 1, 1, 0, 0. Okay, so we have basically 6 ones followed by 2 zeros. Are we doing okay so far with question number 6? Because you can solve this problem. You can answer this question just by running it, okay, which is fine. Okay, there's nothing wrong with that approach. But the way I solve this problem, is exercising what we're supposed to know at this point, So it's probably a good exercise to do it that way as well. And we got a comment in the text channel that says we changed A to 0. Yes, that is how we convert mnemonic into opcode. Because over here it says A is the bit pattern of 0, 0, and then D is the bit pattern of 1, 1. So with ST, what was it again? AD. So Y is register A, and that's why YY as a bit pattern is 0, 0. And then X is D, and that's why the bit pattern XX is going to be 1, 1. Okay, so opcode is referring to the bit pattern that the processor can decode in the decode phase. That is the opcode. And then the mnemonic is what we enter in the source tab of the assembler, because it is way easier to specify the mnemonic compared to the opcode. All right, so Aiden says you can look in the assembler tab or the assemble tab to see what the opcode is. Yep, that is true. But for stuff like this, at least at this point of the class, I think it's a good idea to just try to assemble it a few times, just so that you kind of understand the concept. But I hope you guys are now starting to kind of understand what I mean when I said, when I refer to opcode, which is column A, versus when I say mnemonic, which is, when I refer to column B. Are we good so far? Shall we proceed, or are there any additional questions? Looks like there are no questions. Then I will proceed. Now, if you have any questions or you just need more time to think about something, you can always just direct message me on Discord and just say that, okay, I need a little bit more time, and then I'll go ahead and let you guys have more time. All right, so now we move on to question number 7. So question number 7 says, in addition to specifying opcode, translated from mnemonic, a program can also specify the value of a location using the byte directive. So I use the word directive here because that is the term used by assemblers to refer to something that is not something that is intended to execute, but nonetheless, whatever is the result of interpreting this line will put something into RAM. Okay, so that makes it a quote-unquote directive. For example, the following code allocates and initializes 3 RAM locations to spell out tag, TAK. So we are looking at the ASCII code of uppercase T, lowercase a, and lowercase k in decimal. Okay, so these are basically just ASCII codes. Do we have any questions about ASCII code? That concept should have been covered in CISP310 when they talk about the char type, but I'm not sure because different people kind of teach it differently. I'm not seeing any questions on the text channel, so we're going to move on. Currently, the assembler, okay, that's bad syntax on my part, or bad grammar. The assembler can only accept the use of base 10 unsigned integers, which is not true. Okay, signed will work too. And only 1 byte can be specified per byte line. The byte directive can also be combined with the use of label definitions. This makes it easy to locate specific initialized RAM data, much like initialized global variables. Note that a label is the symbolic name of a single RAM location because RAM is byte addressable, so each location has its own address. As such, in the following code, L3 is the symbolic name of the ASCII code of T. Because L3, which is the definition is here, that is defined to be the location of whatever is going to use that location next. And that turns out to be byte 84. And 84 in decimal is the ASCII code of uppercase T. So that's why, I made this statement here. L3 is the symbolic name of the ASCII code of T. To be exact, it should be the symbolic name of the address of the ASCII code of T. Last but not least, the code of a byte directive can by itself also be a label. The value of a byte directive can also be a label. So I can define something like this. Okay, because if you think about it, it should be okay, because what is L4? L4 is the address of whatever is next, which is whatever this byte is going to take up in RAM. And what content do I want to specify at that location in RAM? Whatever L4 is. Okay, so these two is not a cyclic kind of reasoning at all. Okay, because the first thing we do is to allocate the byte, then we can figure out the value of the label, and then we'll know what to do, how to initialize that location. So it does happen in a specific sequence, which means it is not a loop, it is not a cyclic kind of resolution. You can also write an entire program using the byte directive because you can figure out the binary opcode yourself. The following is such a program. In other words, this actually runs, okay? And unless you want to do the disassembling, to figure out what the opcodes really are, you can, the quickest way to answer this question is to run it, okay? When this program cannot go any further, which means you go ahead and run it in LogicSim, what is the value of register B? You may assume this code starts at location 0, specify your answer as a base 10 integer. All right. So with this question, I think since nobody is really asking about it, most people are concerned about question number 2 and 3. Let me answer this question, but in a long and painful way, which is the best way of doing things most of the time. So in this case, what is the long and painful way to do this? Well, we are going to disassemble. Yes, do it by hand, exactly. Well, except it's not, well, it is sort of by hand, but it's not, we're going to do it manually. All right, so how do we do it manually? Let's go ahead and figure it out. So you might say that, but these concepts we haven't really talked about in class. Well, I haven't talked about the combination of how we can combine the use of the tools and concepts. That is true. But I have talked about the individual concepts and the individual techniques. So it's a matter of combining the things that I have talked about in class in order to solve a problem that we have not seen before. In other words, if I give you a restriction of you cannot use LogicSim to do this, like you have to do on a piece of paper, how are you going to do it? So the first thing I do is I'm just going to copy down the values. So we have 109, and then we have L1, we have 117, and then we have a 1, and then L1 as a label is defined here, and then we have a byte L1 over here. So another L1 is over here. Okay, so that's all I need for now. So the first thing we need to do is to convert everything to hexadecimal, because hexadecimal is very easy to convert into binary. And binary is great in many ways. It's just not very easy to look at. So that's why I like to represent everything in hexadecimal, because it combines the advantage of decimal, which is shorter, but it also has the nice advantage of easily convertible into binary. So we look at 109 and we ask what is the base 16 or hexadecimal representation of this. So I am going to think about this. So we have a 6, and would a 7 work? Let's see. Well, I can also work on this reversed, because 80 is 128. So 70 is going to be 112. So this is going to be a 6 something. 6 times 16 is 96. 109 minus 96 is 13. And 13 is represented by D as a digit. So 109 is 6D in hexadecimal. Now we have 117. And 117 is going to be a 7 something. 7 times 16 is 112. Then we have 5 remaining. So this is 75 in hexadecimal. 1 is easy. It's always just 0, 1 here. So now it is time to resolve what is the label L1. So now we have to count locations. So let me use another column, quote-unquote column, to count locations. This is location 0, 0. And this byte, which is going to have L1 as a value, is at location 0, 1. And I'm going to put question marks over here to basically say this is to be resolved. This is location 0, 3. This is location 0, 4. And this is location 0, 5. And the content is yet to be determined. So how come L1 with a colon does not have an address? Well, that's because a label is really a bookmark. In other words, if you think about each page of your notebook as 1 byte, a label is not a page on your notebook. A label is more like a bookmark or a post-it that you kind of stick onto a page so that it is easier for you to remember where to get back to a certain page on your notebook. So that's why L1 colon, which is the definition of a label, does not have its own location. We got a question coming, so I'm going to wait a little bit for that question. And while I'm waiting for that question, we know that L1 is going to be defined as 5, so we can now resolve those question marks with 0, 5, like such. All right, so the question is why the location 0, 1, then 0, 3? Because TAC is sometimes clumsy and miscounted. Very good. Good catch there. All right, so let's fix those. There we go. Thank you. Very good catch. All right, so this is why I won't be hired as a human assembler. And this is also why we have the assembler as a tool, which is a program. All right, cool. So now what do? We got all of these individual bytes. So now we do the human disassembler. Okay, we look at 60 and we say, hey, this is supposed to be an opcode because this program is supposed to run. So if we try to run the program manually, we have to look at 60 and ask, what mnemonic does it correspond to? So we go back. Oh, this is not horror movie. This is something that is worth money. Trust me. If you can do this kind of thing, using a program, or if you can write a program to disassemble, analyze a program, and figure out how to do a lot of things. I'm not going to say what things. It's worth a lot of money. Okay, it has to do with computer security, espionage, and all kinds of, let's just say, gray stuff. All right, so 60, we look up the opcode table, and we try to figure out in column A, which one is going to match 6D, okay? Now, there will be, at some point, some bit pattern will fit more than 1 rows, okay? But 60 is not one of those. So we can see this is a 6 something, this is also a 6 something, this is a 6 something, this is a 6 something, because they all start with 0, 1, 1, 0, which is 6 in hexadecimal. So now we have to look at the second part, or the least significant portion of the bit pattern, because we have a D, and D is in binary 1, 1, 0, 1. Okay, so that will match this particular one on row 22. So we have an LDI instruction. Now we want to figure out which register is being loaded. So we have 0, 1 for XX, and you just have to do a reverse lookup here. This time we are looking at the bit pattern, and we ask which register. So it's register B. Okay, so now we go back to our little notepad here, and we say this is an LDI B instruction. And what are we putting into register B? Well, whatever byte is next to this, okay? So it is actually 04 or L1, okay? Either one is fine. You can say L1 or 04. So that is the LDI instruction. The LDI instruction takes 2 bytes. The first byte is the opcode, and then the second byte specifies what value are we loading into the specified register. So we got a question coming in, but I'm gonna move on to this one while waiting for the question. Okay, so keep it going. Keep the questions coming. I'm just trying to. This is called. I'm just trying to pipeline and optimize the use of our time. So this is 7.5. 7.5 is 0.1.1.1.0.1.0.1. So we look up the opcode table. Oh, wrong tab here. Okay, there we go. So we look up the opcode table and we ask what is 0.1.1.1 blah 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 corresponding to. Oh, the next one, right? So this is 0.1.1.1, which is the 7. And of course, I cannot remember the least significant digit already. It's a 5, okay, which is 0.1.0.1. So we know the mnemonic is going to be the load instruction. And 0.1.0.1 is interesting because that tells me that XX is 0.1 and so is YY. So I'm using the same register, which is register B, to specify X and also to specify Y. So we have B and then B in parentheses. In other words, the first thing I do is to dereference register B, whatever it is pointing to in RAM. I grab that content in RAM and then store that back into register B. All right. And then the next one is a halt instruction. The halt instruction is at location 0. It has an opcode of 0.1. And that's one that's easy to look up because it's like the second entry right here. All right. So then we have to look up this one here. Maybe, maybe not. Okay. I don't think we have to decode this one because if you look at the program, what it's doing, it is basically initializing register B to a value of 4, and then it will dereference register B, go to that location, which has a content of 0.4, and then use it to update register B, which kind of ends up with, guess what? 0.4. So because I reversed the process of the assembler to answer the question of how I know which opcode to use. In other words, I think the question is asking, how do I know from the bit pattern of 6D that it is corresponding to the LDIB mnemonic? Is that kind of what the question is asking? Yes. Yeah. So the process is to figure out what is the bit pattern, because 6D, okay, I'm going to use it on the side here. So 6D in hexadecimal has a binary bit pattern of 0.1.1.0 and then 1.1.0.1. So now I go back to the opcode table in order to figure out which row has a bit pattern in column A that can be used to describe this particular bit pattern. So we can look up, and anything that starts with 0.1.0.0 is not going to match, right? So anything that starts with 0.1.0.1 is not going to match. So now we have a whole bunch of rows that start with 0.1.1.0. But one of them is only one of these is going to match, because we also need the least significant the least significant digit in base 16. Oh, I take it back. We need the least significant 4 bits to be, what was it again? 1101. So we rule out this one, we rule out this one, we rule out this one, and only this one can match 0.1.1.0.1.0.1. So the XX is actually corresponding to the 0.1, which specifies register B. So that is how I reverse the process. And as such, this process is also known as disassembly. Yeah. So this is really kind of cool because even GDB has a feature to disassemble a program. In DOS or in Windows, there's a program called debug, D-E-B-U-G, that can also be used to disassemble an executable. So it's kind of cool because you can actually figure out the low-level instructions that makes a program go. All right, so I'm going to digress just a little bit, just because we are in this process, okay? So if you are to look up the word disassembler, Okay? You will find descriptions of exactly what it does. Okay, it goes from machine language. So machine language is just another term to refer to opcode. It's all binary, zeros and ones. You can look at it in hexadecimal, but it's not very intuitive for humans to understand. But it will translate that back into assembly language, which is what we know as mnemonics. Okay, so machine language is referring to our opcode, and then assembly language is referring to the mnemonic. So an assembler is a program or a tool that can do that. Now you would ask, why is that important? Okay, so you can look into decompile. Okay, so a compiler is a concept that you should know already because of CISP360. So a compiler basically is a really, really fancy quote unquote assembler that can translate C programs into machine code or opcodes. That's what a compiler does. And can you guess what a decompiler does? It reverses the process. Okay, you give it the object code or opcode, and it will reverse it back into quote unquote a high level program. So a very common decompiler that you can find on the internet is for Java. Okay, so if you look up Java decompiler, you will find like tons of them. Okay, some open sourced, some not open sourced, some are hosted as a website, and some let you download the tool and you can run it. But the reason why there are so many Java decompilers is because when you run a quote unquote Java program, they have to give you the what we call the Java bytecode. And the Java bytecode is the opcode that the JVM or the Java virtual machine runs. The JVM is kind of like our processor. It is a virtual processor that is running in simulation mode, except it is far more powerful compared to our toy processor. So Java bytecode would be the opcode for JVM, and there are programs that can reverse the process. If you give it the Java bytecode, it will give you quote unquote the source code, in the form of for loops, while loops, conditional statements, da 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 da, like that. And there's a question in the text channel: how do modern software apps prevent decompilers from working? There's a tool called an obfuscator. Obfuscator. There we go. So in computer science, obfuscator is referring to a tool that intentionally translate a well-structured program into something that is messy. Okay, it basically takes out the structured nature of a program and use a whole lot of go-tos and just go all over the places. So it is supposed to crank out a program in source code that is equivalent to the input, but when you look at the branching and stuff like that, there's no structure to it whatsoever. So supposedly, okay, this is supposed to break a lot of the decompilers, because the decompilers would look for certain structures, and if it cannot see the template of a structure that it's looking for, then it doesn't understand how to translate the code back into a readable format. I would imagine that it would affect performance a little bit if they introduce additional branches that are not necessary. But I don't think it's going to be a significant portion, because branching is usually quite inexpensive. And when we are talking about the JVM, because it's a software emulated processor, so there's no actual pipelining behind the whole thing. And as a result, branching doesn't cost nearly as much as in a real processor. So I think the cost of performance by obfuscators is not that significant. Yep. So this is interesting because for hackers, okay, in order for a hacker to find out whether a particular program is vulnerable or not, sometimes they use tools like decompilers and disassemblers to find out how a piece of code is written. And by analysis, if they find out that somebody is using string copy, okay, which is not safe, or something to that effect to copy a string, then they would start to they have a starting point to think of how to crack the program. So so all of this stuff here obviously is not directly related to this class, but it is related in the sense that we will start to understand the term of what is a disassembler, what is a term of decompiler, and how a decompiler can be used for at least two purposes. Okay, one is to circumvent copy protection mechanisms, and the second one is to basically hack a program to gain elevated administrator access and stuff like that. Yep. All of this stuff here is very methodical, because after all, a computer or computer programs are extremely mechanical, and the tools that we use to create programs are also very mechanical. So when you want to figure out how to do something, whether it's gray or not, the process is usually very, very mechanical as well. All right. So I can only talk about this, up to a certain point, because beyond a certain point, I'll be talking about something that is actually illegal. Because in the United States, it is illegal to try to crack the copy protection mechanism of a program, thanks to the DMCA. And there are some comments in the text channel. And here I think that hacking is just very fast button mashing and creating pop-ups with random text everywhere. Funny. Well, it's a little bit more than that. It depends on what level of hacking we are talking about too. There are script kiddies, right? Script kiddies, they just download quote unquote a tool and point the tool to a IP address and say, okay, go hurt those servers. Okay, script kiddies. But then you also have people who came up with what is the virus that infected? Oh, excuse me. I think that's my landline. Okay, just ignore the ringing in the background. No, it is not the FBI calling. Okay, so anyway, what was the name of the virus that infected some uranium refinement centrifuge? Okay, I'm gonna look it up because it's a very interesting topic. Stuxnet, that's it. Thank you. Stuxnet. Okay, if you look it up, okay, this is a very fascinating article to read. It is really long. Okay, you can actually go to YouTube too. Just type Stuxnet and listen to how it is explained. But it is interesting not because it is malicious. Okay, I mean, there are tons of viruses and worms out there, and they're all malicious. Okay, they want to crack into your computer. Some want to encrypt your hard drive and then hold you ransom and say, hey, if you want to ever see your data ever again, you have to pay us this much, Bitcoin, blah blah blah. Okay, so there's that. Okay, there are also people who do denial of service attack against banks, right? Because when a bank cannot really handle traffic from their own customers, they lose money. So these people would blackmail banks and say, hey, if you don't pay us this much money, we're going to continue to launch a DNS attack on your servers. Then DDoS, sorry, not DNS, DDoS, distributed denial of service attack on your server. And so there are criminals like that, okay? But this one is by far, okay, much more interesting, because this is a worm that infects Windows, which then in return finds the control software to distribute the quote unquote payload into specialized controllers in basically on a manufacturer floor or nuclear plant in this case. But the target is so specific, it is actually targeting the centrifuge control mechanism of a nuclear program. So a centrifuge, okay, for those of you who have not seen what is a centrifuge, All it really is something that's spinning really fast to create, quote unquote, gravity. Okay, it's not technically gravity, but it is a force. Okay, no, that is not. Okay, so Daniel, the interesting part is it didn't go boom. Okay, so what it did was it would instruct the centrifuge to basically speed up and slow down, speed up and slow down, speed up and slow down rather quickly. Okay, compared to what the centrifuge is supposed to be able to handle, because the centrifuge is running so fast, it's already spinning so fast. So any spin up and any slowdown actually has a significant amount of wear and tear to the mechanical components. So what this Stuxnet ended up doing was basically prematurely failing the centrifuge mechanism. And the centrifuge mechanism is needed to refine plutonium so that it becomes a weapon grade plutonium. And so basically, this particular virus has one purpose in life: shut down a plutonium refinement program that a particular country is running. That's it. Okay. But to do that, the Stuxnet, the part that infects Windows, has, if I remember correctly, 3 zero-day exploits. Okay. And if you do not know what is a zero-day exploit, look it up. Okay, zero-day exploit. Okay, it basically means a vulnerability that is discovered but never published by anyone whatsoever, which is a very rare commodity in the world of hacking. Most hacking is done by identifying older versions of something, match it up to exploits that work on that particular version of whatever server we are talking about, and then launch the attack. Okay, so that is a very common way to crack a server. Is basically just look for something that has not been patched, and then use an existing attack mechanism that is known to work. A zero-day exploit is something that has never been discovered before. Okay, and so there's a comment here that says, "Oh, as if they found the exploit as the update uploaded on the same day." Nope, it is basically just something that is undiscovered. Has never been published, has never been discovered before. Most hackers, if they find one zero-day exploit, they'll use it right away. Okay, because the longer you wait, the more chances that that exploit will be finally discovered and patched. Right, so you don't want to wait. And whoever's behind this particular worm decided to save up 3 zero-day exploits before integrating these into Stuxnet and then launch the actual attack. So the attack pattern is definitely not of a criminal organization. It is not after money. It is after shutting down a national plutonium refinement program of a particular country. And yeah, so people, it's a very short list of who might originate this particular malware. I'll just put it that way. I'm not going to point any fingers because I think those organizations have already pointed to themselves enough that I don't have to do anything. Oh yeah, it's not crazy. This is actually happening on a daily basis now. The cyber world is very interesting, which brings me to yet another two things, okay, somewhat related to this class and somewhat not related to this class. The first one is you can watch in real time, cyber attacks. So all you have to do is to type up, cyber attack world map. Okay, yeah, that should be enough. This is one, FireEye is one, and you can even, there are open source ones that you can host on your own server if you want to. Yeah, so look at that. I think there's one open source one that has sound effect. Okay, so look it up. Sound effect cyber attack world map. Okay, and let's see. I think it is listed as one of these. Norse is the original one. It is not working anymore, I think. Checkpoint, these are all commercial ones. Nope, nope. Okay, I cannot find it right away, but there's one that is open source and it has sound effect. It's really funny to watch. So that's one. And the other thing I want to point out, this one is definitely related to students at Los Rios. And let me find where I put that thing. Give me a second here. I'm looking on the side. So you might want to mark down November 12th in the morning at 10:30. I'll give you the flyer in just a moment. I'm looking it up right now. All right, so that's ARC, and there we go. Cool. And I'm just going to put the tab over. Let's put it over here. There we go. All right, so I will put a PDF version of this, in today's text channel and pin it. So this one is interesting because we are going to have 3 guest speakers. General Army Major General E has talked about computer security already on campus. I think that was last year or sometime before COVID-19. So he is, according to this, the assistant to the director of DISA, DISA, and DISA stands for Defense Information Systems Agency. You can kind of look at DISA as the IT department of the Department of Defense. So instead of having Army running their own network, Navy running their own network, Marines running their own network, and Air Force running their own network, particularly the Air Force, they are now consolidated into one single agency running the IT infrastructure for all the branches of the Department of Defense. So they are going to talk about cybersecurity. They're going to talk about the Fourth Estate Network Optimization Project. I believe that is basically the consolidation of all the IT, all the networking, and all the infrastructure for the entire Department of Defense. And last time when General Yi was here, they definitely talked about internship opportunities. And those internship positions are all in Washington, D.C. So you're going to have to travel to get to those opportunities. And hopefully they will also talk about what it is like to work at DISA, and also, what does it take to be employed as a, cyber security expert. You can see the qualification of Serena Chan. She has a PhD. And so depending on at which level you want to work, okay, you might want to pursue a higher degree, okay, like a master's degree or a PhD, in order to get into this particular industry. So I think it's going to be very interesting. The date of the event is Thursday, November 12th, and the time is 10:30 a.m. So it's going to be a Thursday, and we have class in that evening. But if you have time in the morning at 10:30 or so, you can join the live stream with this link over here. It's already scheduled. It's just a matter of me hosting, the whole thing and getting things distributed on that day. So you might find it useful, and you may not find it useful. Okay, if you don't have time, it's not a big deal. But on the other hand, if you want to know more about cybersecurity, employment opportunities in cybersecurity, which I think is is going to be booming. Okay, there's no going back. In terms of those employments, then you might want to join us. On November 12th, because I think this is a great opportunity to get more information. So I'm going to leave it up here so I can later on download the PDF and put it into the text channel today. All right, so I guess I did digress quite a bit, because all I really wanted to do is to explain the answer as 4. Yeah, that is a typical thing that I do sometimes. All right, so getting back to here, okay? So question number 8, this is number 7, or is it number 8? Oh, just number 7. So question number 7 has one really direct way to answer, which is just copy, paste, run it in Logisim, figure out what is in register B, and you're done, okay? But this way is more interesting, okay? Because it is still using everything that I have taught so far. I have not used anything that I haven't taught, other than the techniques of how to combine the knowledge that we have already been exposed to. But this is the sort of thinking that will get you jobs, okay? It's the problem solving skills. So let me confirm that this is actually correct, okay? So I'm gonna check on the scores. 1 of 1, 1 of 1, 1 of 1, 1 of 1, and 1 of 1. So the way I answer question number 7 is correct. And thanks to, I think it was Oan, okay. Thanks to Oan, who noted that I jumped from 0, 1 to 0, 3, bypassing 0, 2. Yeah, because otherwise I would have written down 0, 5 here, which would be the incorrect answer. All right, so let me just give you guys the chance to kind of catch up and ask questions. Go ahead. Or have I lost, a good portion of the class already? Probably not. The labs collectively, if you add up all the points of all the labs, they only make up 20% of your grade. So even if you were to kind of mess up one, it's not gonna be that significant. And we have another text coming in, so I'll wait a little bit over there. How to run the code in question 7? Oh, that's easy. Um, you literally copy and paste. Okay, so you copy, paste it into the assembler. Okay, go to the source tab and paste it into column A of the source tab. Extra stuff is not going to hurt it. Okay, you just need to make sure the first portion of whatever program here is the content. You go to the RAM file. This is the same process that we have already talked about of how to run a program given the source code, right? So we download it and just save the file. Don't open it. So we save it. I save it as mystery. There we go. Okay. So we save it and then we switch to Logisim. Okay. Let me close one tab here and then switch to Logisim. Go to the RAM component. This is the stuff that was already done, in a previous lab. So I'm assuming people already know this process. So we load the image and specify the same file, which is mystery.csv. Program is here. Turn on simulation by turning on ticks enabled, like that. And then we just have to wait until the hold pin is a 1. Then we can stop the simulation, like so. And then we go check register B, which is an output pin from the processor. It is up here, and it is basically 4. Okay, 0, 0, 0, 0, 0, 1, 0, 0 is just 4. So I hope that answered the question in the text channel. I mean, you just basically assemble the program like any other program. There's no difference between this program, which looks really odd because I did not use any actual mnemonics. Okay, so to answer that question, is that 4 in hexadecimal or binary? What digits can appear in a binary number? Yep, that's right. So that means it cannot be a binary number. So that means it is either in decimal or in hexadecimal. But since only the least significant digit is a non-zero and it is not more than 9, so that means whether it's hexadecimal or decimal doesn't really matter because 4 is 4 in both. There we go. Yep. Cool. All right. So what I'll do today is I'm gonna, well, with whatever time is remaining, which is 15 minutes, that's more than enough time to illustrate what I want to illustrate, is to show you a new tool to run programs in LogicSim. And I know some of you are thinking, oh no, not another way to run programs. We got enough already on our hands. That might be the case, but this new tool is really cool in many ways. So I'm going to introduce, you can decide whether to use it or not. You can say, I don't want to use it now, maybe later. That's perfectly okay, not a problem. All right, so let me, let me go to my, oh, come on, where is it? I just ran past where I want to stop. There we go. Too many tabs opened. So this is my mouse pad, and I'm going to repeat the same program here. There's only one caveat to use this tool. The first instruction has to be a no-op. So don't ask me why it is a bug in LogicSim, and I haven't spent the time to try to debug this one. Eventually, when I have time and I run out of fun things to do, I will do that, but not yet. Okay. So the first instruction has to be a no-op to use this approach. And then I'm just going to repeat this program, okay? LDIB with L1. I'll use a label because labels are easier to use, okay? LDBB, like that. And then a halt instruction, label L1 is defined here, and it is just byte L1 itself, okay? So basically, other than the no-op instruction, this is exactly what the bytes are specifying. But this time I need a no-op here because of a bug in LogicSim. I have to start a program with no-op to use this approach. So I just copy it. Okay, right-click, copy, go to source, and then paste. And paste this right here. There we go. Oh, okay. Control V. There we go. All right. So the program is pretty much the same as the one before. It's going to do exactly the same thing, except it's going to have 5 in the register because I have just offset all the bytes by 1 by having an additional no-op at the beginning. Then we go to the RAM file, and then we go to File, and then we specify download, comma separated value, just like usual. Save the file, and I will even save the file as the same name as last time, which is mystery.csv, and use it to overwrite the file that I already have. Okay, so this is it. Okay, I'm done with creating the file. The magic of this approach has to do with the command line tools. So this means you kind of have to learn how to use the command line in order to utilize this tool. So I'm going to run LogicSim by hand on the command line this time. And I have to make sure that I don't have LogicSim running in GUI mode. And I believe I closed that one already. All right, so now we just run LogicSim the usual way. Okay, so the command is already up here. So I can just kind of copy it. Java-jar. And then we specify where we have put LogicSim310.jar. Okay. So in Windows, you have to use backslash to separate folders in a path. And also you don't have a tilde symbol to designate the home folder. So you kind of have to look it up, how to specify a particular folder in Windows. The other way is to put everything into the same folder. So don't have to specify a full path. You just have to say, oh, okay, everything is in the same folder. You just need to specify the file name. So I'm going to leave it up to you guys to learn how to convert file path in Windows as opposed to in Linux. So this way is not going to work in Windows for sure. Okay, then we have to specify the path to processor 0003.circ. Okay, so now we have documents, CISP310, processor, and processor 0003.circ. Okay, now the full path to the jar file and also the circ file has to do with where I decide to put my files. So where you're going to put your files is entirely up to you. So copying this path is not going to work at all, in your case, unless you structure your folders exactly the same way as I do, and you're also using either Linux or Mac OS X. So this part is just going to start up Logisim in the GUI mode. So now here comes the magic part. The magic part is to specify dash tty table. Okay, so this is telling Logisim do not start in GUI mode, and instead, run it in batch mode. Okay, I'm just going to call this batch mode, which basically means it's not going to give you a user interface. It will run the program, but its output is going to be captured in a file. Okay, and then we're going to specify dash load, and then we specify the RAM file. Okay, so dash load allows you to specify when we run this program, I want this file to be loaded into the RAM component. Okay, so in this case, I have it in temp/mystery.csv. And I think this is it. Okay, so if I just run it like this, you just see a whole bunch of zeros and ones. Okay, now all the information is already here, but it's very difficult to decipher. Okay, this is basically the same thing as the log file or the logging capability that you need to use for the lab that is due next Tuesday. And please, please, please work on this not on the day it is due. Okay, that is just not a very good idea. So work on this as early as possible so that you can ask questions before the time or the day it is due. Okay, because I find that a lot of people ask me questions at the very last minute to try to get a lab done, and sometimes I got other things to do like cook, right? So I may not be able to answer those questions in a timely fashion. So just start early. All right, anyway, so getting back to here, then you use the greater than symbol. This works in Windows as well. Okay, so the greater than symbol is known as the redirection symbol. So whatever output of this program is now going to be captured in a file. So I'm gonna just name the file that will store the capture as log.tsv. The reason why it's called a TSV is because it is tab separated value. Okay, CSV is comma separated value, and then TSV is tab separated value. Okay, press the enter key, and it seems like nothing happens, and that's because all the output is now captured into the log file. You should make tag separated value. That is funny. Okay. All right, so TSV is useful. So now we go back to the folder where the tools are located. So we go to the share folder, and this is not the right one. This is the wrong class. So we go to the CISP shared folder and then the processor subfolder. Okay. And we're going to bring up a tool that is called the trace analyzer. There we go, trace analyzer, like this one. And I think some of you may want to bookmark tonight's lecture, particularly the time when I started to talk about this tool. And it's not too late to write down an entry right now of October 29th. And the time is, I would say when I started to talk about this, it was about 8:05. So you might want to write it down because the instruction to do this It's a little bit daunting at first, but once you have done it a few times, it's not so bad. Okay. So in the trace analyzer, first of all, you have to make a copy first, okay? Because you cannot just overwrite the one that I have. And don't even try to download it and run it in Excel. It's not going to work, okay? So this will only work as a Google Sheet document. So you go to File, and then you go to Import. And you can only do this part when Sheet 1 is the current sheet. So you got to make sure, over here in the tab, you are selecting Sheet 1. Then you go to File, you go to Import, and then you specify Upload, and you will go find the TSV file that we have just created, which is log.tsv. It's really handy to be able to sort the file where the most recently modified file appear first. So then you click Open. All right, so I know most people would just click the button to say, let's just do it, right? No. We don't want to just do it because there are a few things we have to specify here. We need to replace current sheet, choose the separator as tab, and also turn off convert text to numbers, dates, and formulas. Okay, so for your convenience, okay, when you re-watch this video and you want to take your own notes, you might want to take a screenshot. Okay, take a screenshot, paste that screenshot into your own document. So this way, it's easy for you to refer back to what options to choose and what options not to choose before you click on import data. Because if you choose the wrong options, it's not going to work. So now we click import data, and you will see the hourglass or the progress bar to kind of stick around for a little bit. This is a pretty short trace, so it's not going to take long. Wait until we have something that has like several thousands of rows to process. Then it's going to take some amount of time. Then we go to analysis, okay, which is doing all the magic of decoding all those zeros and ones into something that we can actually read. So we got a question coming in the text channel. I'm keeping an eye on it, but I will continue to talk about this. So column A is the program counter. It's telling us where is the opcode that we are executing. So 00 is basically saying we start with the location 00, which is our no op instruction. And then 01 is corresponding to the LDI instruction. And then 03 is corresponding to the LD instruction. And then 04 is corresponding to the halt instruction. Okay, so I see a question in the text channel. How do we have access to Google Drive for the assembler file? Not quite sure what that is asking because you always have access to it. You just have to make a copy of the file first. I believe we talked about that quite some time ago, how we go there, go to File, and then you click on Make a Copy. Or you can do it from the folder perspective, that works as well. So you just go to, a particular file, right-click on it, and then you say, oh, that won't work because if you click this make a copy, it will make it in the same folder. Yeah, it doesn't ask you where you want to make a copy. So you have to open the file first and then go to File, go to Make a Copy. Make sure you specify the destination folder because otherwise it will try to make a copy in the same folder. I believe we talked about that already. Yeah, it should work the same way as what I do here. Okay, so getting back to the explanation. So column A tells us, the location of the opcode that we're executing. Column B is very specific. It talks about, where in RAM are we reading from. So the format is in a pseudo C format. Asterisk 02 means we're dereferencing location 02. And then this is intentionally using double equal because we are not changing that location. We're simply saying whatever is at location 02 is 05. Everything is in hexadecimal in this analyzer, okay? Column C is not going to be used for a while, okay? Until we actually do something that will overwrite RAM location, column C should be empty. Column D is telling us, how we are updating registers. So we can see in this case, register B is getting a new content of 05. So make sure that you note the difference because we have double equal here, basically just to indicate that, oh, we just read location 03, it has a content of 75, as opposed to this one, which is indicating that register B, not location B, is updated to a new content of 05. So that's it. Okay, so this gives you a quick summary of when your program runs, what happened to RAM locations, and what locations are the opcode correspond to opcodes that we execute. Now this program is pretty simple. Okay, this program is a fairly straight line, which means it has no branches, there are no loops, no conditional statements whatsoever. It's a straight line. Okay. So that means it is not as important to use this tool. But when we start to have subroutine calls, loops, conditional statements, recursion, and stuff like that, this tool becomes very, very useful to debug programs. The kind of symptoms you see when you have bugs in assembly language programs is going to be something that you haven't seen before in C and C++. And trust me, that's going to be a whole new experience to for most of you. And having a tool like this, to be able to capture every single update to the registers, every single update to RAM locations, and it will also remember and trace the location of all the opcodes that we execute, is going to be super handy. Now, the fact that this is inside the spreadsheet makes it even more handy because you can search. Okay, you can search for a particular pattern within a spreadsheet, and that is without using any custom scripts. Okay, so you can go to edit, and then you go to find and replace. Make sure you don't hit replace because we don't want to change anything. But if you specify what byte pattern in hexadecimal you're looking for, that will make it super easy to locate something even when you have thousands and thousands of rows in a trace. Okay, so that is really helpful. And for those of you who say, hey, but I know how to do Google scripting, which is just JavaScript, you can even enhance this tool further by going to Tools, go to Script Editor, and then you can just knock yourself out writing your own script. Okay. The only caveat is if you do that, if you do anything to extend the tool that I have here, then the next time I update this tool, you're going to have to copy the script from your modified version to a copy of what I have updated already. So that's the only caveat, if you want to extend this tool to do more by writing your own script to analyze, whatever tab you want to analyze. So when you have time, okay, for this particular homework assignment, you can go ahead and try to use this tool. The only thing you have to really have to remember is to start with no op, okay? Because if you don't start with no op, then the tracing mechanism on the command line is not going to work. So you have to start with a no op first, and then the rest of the tool, the rest of what I demonstrated tonight should work. So to kind of to repeat my point earlier, you have to make a copy of the assembler. Okay, so go to File, go to Do Not Download. Download is not going to do you any good at all. Okay, so you gotta have you gotta go to make a copy, and then when you do that, make sure that you go to the folder part, and then navigate all the way back to your own drive. Okay, and then specify where you want to put it under your own drive. Because if you don't do that, it's not going to be successful. And then do the same thing with the trace analyzer so that you have your own copy of the trace analyzer. Once you have your own copy, close the one that I have, okay? Because the one that I have, you can view, but you cannot change a single thing. So don't try to use the one that is inside the share folder. Make a copy first, and then use the copy that is in your own drive. All right, so we are running out of time today. It is 8:25-ish. Okay, so do we have any questions? We covered actually a lot of material today. I know some of this material is not strictly related to this class, but I think it is probably a good thing to introduce you guys to those concepts. Nope, I'm not taking roll today, and there's no new lab tonight either. So we are basically just continuing to work on the lab that we started on Tuesday because it's due next Tuesday. And my suggestion is to work on it as soon as possible because it's not a easy lab. And it does, you also need to refer back to the lecture on Tuesday in order to understand how to log and also how to reset the log um, in Logisim itself. Now, if you want to practice what I just showed you today, you can do that too. Just kind of keep in mind that you might have a slight learning curve of how to run your Logisim on the command line. But this investment is going to pay off. Okay, I cannot tell you guys to learn VI, okay, the editor that I use, because the payoff is kind of questionable. Whether you get enough payoff within a semester, that's kind of questionable. But when it comes to this particular tool, which is the trace analyzer, I can tell you right away that it's going to pay off in this semester. So just bite the bullet, learn how to do command line stuff in Windows, Mac OS 10, or Linux. You can also use the text channel of Discord to kind of work with other people, because I think someone else may know more about command line stuff. If I see a question, I will try to answer that. But I think there are several people in this class who are quite proficient with command line stuff already in Windows, so you might get answers from those students. So that's all I can say. Is to try the tool if you can. But there's a learning curve to it, but it's worth it. If you do not have time, then you can just follow the instructions in the lab, combine it with what I talked about on Tuesday, and you will still be able to finish the lab. It's just, it's up to you. Decide which way you want to go. Cool. Any questions before we stop the live channel? No questions. Okay. Once again, I think it's important to kind of, even if you're here in the synchronous session, I think it is important to watch the video again, okay? Because there's a lot of concept that I have covered, not counting the digression to computer security. There's still a lot of stuff that I've covered. And as you rewatch it, okay, use a bookmark system to time mark stuff, okay? And I think you guys know. If you don't, you can Google it. You can make a link to a YouTube video with a time mark integrated into the URL. So this way you can maintain your own spreadsheet. Now you can use Google Sheet, you can use Excel, whatever. It doesn't matter. But you can basically now have a table of links into YouTube videos going to exactly the spot that I start to talk about something. So this way, when you need to review something, okay, it's much easier. You don't have to search, over 80 minutes of stuff, okay? You can just click and you're right there, right? So try to use those tools, because they're all available to you for free. And that's all I am going to say tonight, if there are no more questions. So there's no row taking today. Okay, I'm just gonna type here, no row taking tonight. And with this stuff here, people who do not watch the video, not participating in the synchronous or the asynchronous, session, I think there's really just no chance that they can get the lab done or to understand the concepts. So I think there's no need to take roll at this point. Cool. And I have one question or one text coming in, so I'm gonna wait for that before I stop the voice channel. And I'm waiting. Okay, so maybe there is nothing. Oh, there we go. Okay, so thank you. Oh, well, you're most welcome. So you guys have a nice weekend, and I do encourage you to try to do the lab sometime tonight and ask questions. But then I'll see you on next Tuesday. Alrighty, good night, and have a nice weekend. Stay safe and healthy. I'll see you on Tuesday.